All right. So now that you have made your first 4 models of our solar system and the planetary motion, gravity and orbits within, I wanted to put together a few little sets of notes to kind of summarize what you've figured out, because each group did a different model for model 4. And so I wanted to kind of bring together what all the different groups put together. So here are the big trends that I saw. And I kind of put together some basic notes on what is the factor and then what is influencing it. Okay, so the first, and then we're going to call this the orbit and gravity model factor notes. So if you want to add this on page 38 or whatever your next page is, that'd be great. Okay, so first, we have surface temperature. So some of you did a model based off of the surface temperature on the planet, and you found that that was based on the following things. Number one, it's based on the distance from the sun. And it's based on the distance from the sun based off of the inverse square law. So remember, the inverse square law is that the surface temperature would be inversely proportional to the distance squared. Remember that butter gun thing, where as you get further and further away, it's spreading out over a greater and greater area. So that's like the distance squared leading to a lower temperature. Okay. All right. Another thing that surface temperature is based off of is atmospheric pressure and composition. So certain gases trap heat closer to the Earth. We call that the greenhouse effect. Those are greenhouse gases. So on the Earth, we have 1 atmosphere of pressure, and our atmosphere is 78% nitrogen and 21% oxygen and 1% argon, or 0.92% argon, and then like a smattering of little things. So like 0.03% carbon dioxide, for example. On Venus, which is the next closest planet to the sun from the Earth, Venus has 92 atmospheres of pressure, and their atmosphere is 99% carbon dioxide. So that's a super intense greenhouse effect. Any heat that gets into the surface of Venus, it's not coming back out. Well, I mean, some of it will, but very, very little, because that atmosphere traps all the heat close. So the atmospheric pressure and the composition makes a big impact on surface temperature. That's why Venus is such an outlier in terms of the pattern of temperature. And then finally, the third thing that matters is the obliquity to orbit. So obliquity to orbit is the tilt of the axis of rotation. So the Earth, for example, is sitting at a 23.5 degree axis off of totally vertical. So we say that it has an obliquity to orbit of 23.5 degrees. Now, what this controls is seasons. So this leads to seasonal variability as different hemispheres face the sun and get that direct vertical sunlight. So, you know, if the sun is coming in like this, boom, 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 then when the Earth is facing like this, the parts that are getting the most direct vertical sunlight here would be, and just to be clear, here is the equator going there. So right now, this part of the Earth is going to be in summer. It's going to be the hottest. And then the parts that are the coldest would be down in like this zone here, where it's getting really colder. So that's our seasonal variation. And you can see based off of where the equator is, that's the northern hemisphere and the southern hemisphere, right? The northern hemisphere is in summer, the southern hemisphere is in winter. When the Earth goes around to the other side, it flip-flops. Okay, another factor that we all investigated was the orbital velocity. So a bunch of us made models about orbital velocity, and what we found is that there are a couple factors that influence orbital velocity. The first is distance to the sun. That could be the radius of the orbit. And then the other one is the orbital period, which is capital T, and that's measured in time in days. So here I've drawn a little diagram showing R is the radius, but we're actually going to call it D for distance to the sun. V is the orbital velocity, and then T would be the period, the amount of time it takes to do one complete orbit. So that would be, let's see, this guy all the way around in terms of time would be t. All right, so we can solve for this by starting with a velocity equation. Velocity is equal to distance over time. In this case, because it's doing a circle or close to a circle, we can say that the distance is the circumference of the circle, and the equation for circumference is 2 pi r. In this case, we're using d for the distance to the sun to represent the radius. So it becomes 2 pi d. And then the time I need is in days. So once I have that time in days, I can convert that time in days by multiplying by 24 hours in a day. That'll cancel days. Then I can do 60 minutes in an hour. That'll cancel hours. Then I'll do 60 seconds in a minute. That'll cancel minutes. And that'll leave me with my time in seconds. So I end up with the total distance divided by the total time in seconds. So the overall velocity is going to be 2 pi times the distance over 8,000 or 84,600 t, or the period is equal to 2 pi d over 84,600 v. So I can solve either way there, and that'll give me the answer in assuming that it's giving me the distance in kilometers. It would give me my answer in kilometers per second, or it could be in miles per second, right? And then t would be in seconds. All right. Or sorry, it would be in days, and then finally, our last factor that some of us solve for is acceleration due to gravity. So acceleration due to gravity is based off of two factors. It's based off the mass of the planet and the radius of the planet. So this would be the acceleration due to gravity on the surface of the planet. And then I can start by taking two equations that we already know about. The first is the force of gravity equation. The force of gravity is equal to gravitational constant times both masses over the radius of the planet squared, or the distance between the two masses, which in this case is the radius of the planet. And then I can also set that equal to the force of gravity is equal to the mass times the acceleration due to gravity, because I'm trying to solve for the acceleration due to gravity. When I put those together and set force of gravity equal to force of gravity, I get g m1 m2 over r squared equals m a sub g. M could be the same as m1, the mass of the first object. So those cancel because I have one on each side of the equation, leaving me with the acceleration due to gravity is equal to the gravitational constant times the mass of the planet over the radius of the planet squared. So a sub g equals g m planet over r planet squared. So those are three factors, and it shows like what it's based off of and how I could actually create a mathematical model to show that. So those are a few, and that'll be really helpful as we shift into model 5, where you have to select some things that are based off of these, like what could you predict given certain things? Hint, hint, hint. You could predict at least 3 certain things, and then maybe one more. Perhaps you could predict something like that, given these things. Cool, so for model 5, that might be a helpful starting point. Best of luck as we shift into model 5.